Hi friends, this is PPH 3802 Unit 2 by Dr. M.R. Gadhvi. In the present lecture, we will be focusing on the one of the physical property of nanoparticles or nanophase, and that is the melting point. In general, it is many times observed that melting point is drastically varying with the particle radius. So, if the radius will be decreases, the melting temperature was initially it remain invariant, but as it is reduces a lot, I mean it is comes around 5 to 7 nanometer radius, the it is drastically reduces. Particle size is mean the diameter. So, in some books also you are finding out the melting temperature versus the diameter. So, you can having the so here the particles sizes reduction is observed with respect to the depression of the melting temperature, where you have observed after hundreds nanometer the variation is invariant. That means it is almost like a melting point of a bulk. But if you reduces the 100 nanometer and so on, you are finding out the drastic variation in the melting temperature. So, as the particle is smaller, the variation would be larger. Now, basically the melting point decreases is underlined with the idea about the context of the bulk system, because of the surface energy is increases. Now, why surface energy is increases? Because in case of a bulk to nano, the surface area would be increases compared to the bulk property or the bulk behavior. So, the bulk material does not have a large volume, I mean surface to volume ratio, but in case of a nanophase or the nano system, you having a large volume to surface ratio, and then the available number of the atom on the surface would be increases, and therefore the variation of the melting point is underlined. Okay, so melting temperature decreases as the size decreases in the metal nanoparticle. So, we are limitize our case on the nanoparticle, especially with the metal cases only. The strongly dependence in size as well as one more parameter, that is shape. So, we would like to cover both the one. The most standard shape, that is the spherical one, and another one is any kind of a shape. So, in general we say it is a non-spherical, but we will definitely put a limitations on our model also. So, actually the melting temperature depression results from a surface to volume ratio. It observed that surface area of a nanoparticle is different shape will be different even in the identical volume. That means if the volume will be same, you can have a different shape, and if the shape will be different, then your available surface area will be different. If available surface area will be different, available number of atoms on the surface will be different, and that results the variations in the depression of a melting temperature. Okay, so one of the simplest technique to measure or to speculate the melting temperature by calculating the cohesive energy. Cohesive energy, that means the energy which hold the atoms together, the binding energy, the energy associated to the bond. That way you can understand. Okay, so cohesive energy increase with the size of the particle. It's do obvious that as the cohesive, I mean the particle size is increases, available number of atoms within that is more, and therefore the cohesive energy, that means the bonding forces within them, that would be increases. So, it is directly proportional to the available number of atoms. If the particle is very large, the cohesive energy approaches to the bulk. माने 100 से अगर ज़्यादा आप नैनोमीटर वाला पार्टिकल चूज़ कर रहे हो, तो नेचुरली इट विल बी ऑलमोस्ट सिमिलर लाइक अ बल्क material rather than a nanophase. That means you cannot observe any significant variation of a nanophase variation or a variation due to the surface to volume ratio. Let the nanoparticle diameter is d and the it composed of a n number of atoms having the diameter is small d. So, do remember capital D for the particle size, small d is for the number of diameter of the atom within the particle. So, particle surface area, if I will consider as a spherical, then S0 is considered as a particle surface, then it would be pi d square, okay, or you can say the 4 pi r square, it is one and the same. So, instead of a 2r, d is equal to 2r and that will be the square, and that is what the surface area of a n atoms is within that, and therefore I can say it's a, if this both, that means S, that is the area of a particle, and this is the area of atom which is within this particle, and if such n number of atoms are there, then the total surface area of this whole n number of atoms, that would be equal to the again S. So, ultimately I would like to compare the particles surfaces which is made up of all n number of atoms. Okay, so let this all atoms are almost on the surface, because as it is on the nano phase, naturally the atoms will be larger on the surface compared to the core atoms. And suppose there is some core atom, let for instance, do not consider or neglect them. Now in this case I can compare the volume of the particle, that is exactly equivalent of the n number of atoms volume, and therefore I am considering with the 4 pi by 3 pi r cube or d by 2 raised to q. This d is the particle size and this d is the atom size multiplying the available number of atoms. So, if I will equate them, I may having the find it out what is the n in terms of the ratio of capital D to the small d raised to the cube. So, this is basically number of atoms on the particle or the atoms which compose the particle or rather the nanoparticle. In this situation, the variation of the surface could be calculated by equation 3, that is delta S, that is n pi d square minus pi capital D square, and therefore equation 3. Let En be the cohesive energy of n atoms, and that equals to the surface energy of a solids. So, because I am considering the entire particles are on the surface, so naturally if En is the cohesive energy of n atoms, then naturally that would be exactly similar to the particle cohesive energy. And if I find it out that the surface area is some around delta S, that is equation 3, then the surface energy per unit area is, let us say, gamma 0 at a 0 Kelvin, then the total surface cohesive energy associated to the change in the surface, that would be given by delta S multiplied by gamma 0 at 0 Kelvin. फिर से अगर आपका cohesive energy is En for n number of atoms, as there is a change in the surface from a nano phase to the bulk phase, or the number of atom surfaces to the particle surfaces, and we are mimic them, that all particles are on the surface and therefore there is a variation in the surface. Agar the surface energy per unit area is 0 Kelvin, is at 0 Kelvin is gamma 0, then gamma 0 should multiply with that particular surface, and that would be my En. So, that is equation 4. So, En is equal to the delta S multiplied by delta S value, we will get it from the equation 3, and then further I will be taking out n as a common. So, I will having the equation similar to that, where it is a d square by n. And now if I will check it up, the cohesive energy per atom volume, that means if this n is I am dividing with my LHS, that is En, that is the cohesive energy divided by the n, N is the total number of atoms. So that means energy per atom, and therefore I can write it out E1 because it is the energy associated to a one atom, and that would be given by equation number 5, pi gamma 0 small d square into bracket 1 minus small d upon capital D. Okay, the lattice parameter can be also involved here, and this I think you had learned in maybe your undergraduate study, some around in SY PSC, the calculation of the packing density of atoms within a precise structure. We will choose a very standard cases. You may have a chance to prove any one of this. It's easy, one step geometry. Atomic packing fraction, let us I have chosen for the BCC, then the equation is number of atoms multiplied by the atomic volume divided by the unit cell volume. Okay, and from that you can have, let us say it's 100% packed one, so I am mentioning that let there is no voids. Ideally it's not true, but if there is no void, then you can equate your unit volume is equal to your available number of atoms volume. So that what I am doing, it's a cube versus that means a cube I am taking here. So this is, let us say it's a 1. Okay, atomic packing fraction 100% packed, no voids, and therefore I can equate this, and from that I can find it out. The D is equal to 3 by pi raised to 1 by 3 or cube root of 3 by pi into A. That is what's first one. I ask you to just prove it the rest two, that is the FCC and the HCP, that is a hexagonal close packing, face centered close packing, cubic packing, and so on. Okay, so let's move ahead with that same logic. So in nutshell, we can introduce the lattice constant within your correlation with the lattice constant and the sizing of the atom. So there is some correlation of wherever you have seen in your previous equation like a small d, that would be replaced by the lattice constant. So that is also possible by the equation 6. Anyway, so we are not going into detail, but that could be your exercise, just remember that. And the equation 2, that is the ideal case. So the necessary to add a k factor, if it's a 100% consideration that all atoms are on the top surfaces and there is nothing in the core, then naturally it's a true. But we are knowing that it is not the practical appearance, or it is not the happening in practice. When you are having the particle as a spherical or in any shape, naturally there has to have a certain number of atoms within that. It is a general ratio that you may having a more than 50% of the atoms on the surface, but rest are still near the surface or inside the surface or maybe the second layers, and therefore some correcting factor I am introducing into my last equation, that is equation number 5. And therefore since I am correcting the equation, so instead of a E, now I am writing out the E dash. E dash is the corrected value of the cohesive energy of my nanoparticle, and therefore I am just multiplying with the k, nothing else. So k pi gamma 0 d square into bracket so and so. Now suppose this d is too large, so that is what from the very first or second slide we have seen, the after 100 nanometers there is not variation a lot. So if d is too high, then this factor you can neglect it out because it would be very very small compared to 1. So there is no contribution of this. So neglect this, the second factor of the bracket. So in that case, that would be, I have given the statistics also. So in case of a metal, if small d to capital D is about 10 to the power minus 7, if the particle is very very large or maybe 100 nanometer and so on. If you look at here, this is a few nanometers and this is 100 nanometers. So this is 10 to the power minus 7 power will appear, and that would give me the relation from the 7. I am just eliminating the last factor, and that is will be the k pi gamma 0 d square. So this E dash I am replacing by EB. B stand for the bulk property. So EB is the cohesive energy of a bulk one. That means if my particle is too large, the cohesive energy associated to that would be EB. There is no significance of the second factor of the equation 7. Okay, but if the particle size d in the range of a nanometer or it is a very smaller one, this factor is become significant because it is just in the order of 10 to the power minus 2 to 10 to the power minus 1, and in this case you cannot neglect it. So equation 1 would be in the shape of this one. So now the E dash I am replacing by the EP, with that means the nanoparticle, and rest part is as it is. So this is the very first part of equation 7 if you look at here. So this is equation 7 is just rewriting here with a flavor of equation 8, because the first line of your k pi gamma 0 d square is nothing but your equation 8, and therefore that is replaced by the EB. That means the nanoparticle cohesive energy is 1 minus d upon capital D times of the bulk cohesive energy, and that is what our main aspect in the next calculation. Okay, so let us introduce. So now we reach to the cohesive energy of the bulk as well as the cohesive energy of a particle. Now let us introduce the factor which is about the D-shaping or the understanding of the shape. That means our idea is, in general, wherever the discussion is going on for any shape, the most easiest geometry would be the spherical. So here also we will introduce the same idea, that we having the shape factor is alpha, which is the ratio of S dash upon S, where S dash is a non-spherical one and S is a spherical one. So S, that is why I am writing out the 4 pi r square, that is the surface area of the most spherical nanoparticle. And suppose the particle is not spherical, that means it is a not spherical, then it could be of any shape. So I am writing a non-spherical oblique any shape, then that would be the S prime. So that's S multiplied by alpha factor, and that would be alpha into 4 pi r square. The capital R is the radius of the nanoparticle. Remember that small as the capital D is the diameter of a particle and small d is the diameter of an atom. Same way, the capital R is the radius of the particle and small r would be the radius of the atoms which is composing the nanoparticle. Assuming the atom nanoparticles are perfect sphere, then contribution of the particle surface area by some around pi r square. So this is a small r, that is the radius of atom. Let we having n number of atoms on the surface. Again coming to the tagline that the available number of the atoms on the surface is more, and therefore I am saying that n is the number of atoms on the surface which equal to the ratio of the surface area to the pi r square. So what exactly I am doing? The area, the particle surface area is divided by the atomic area or the area consumed by an atom, and this is the area which is of a particle. So if I will take that one, so that n will give me a number of how many number of atoms are on the surface. On an average, it is observed is always 25%, because if I will consider a spherical geometry, there would be a many voids on the surface will be developed, and I don't have too much space to occupy the many atoms. Anyway, so let us consider the volume V of a nanoparticle is equal to the spherical nanoparticles, and therefore it's a 4 pi by 3 pi r cube. This is the atomic volume. Okay, and therefore I can say that n is equal to this surface, so that is your S dash. So the D shape or the other than the spherical one, so it's a alpha 4 pi r square divided by the area of an atom, and therefore this is giving you a number of atoms on the particle which is non-spherical or of any particular shape. I repeat, equation 10 is giving you number of atoms on the surface of a particle which is not spherical or which is in the other shape. So, if I consider volume as a V is a 4 pi by 3 pi r cube, then if I will take the ratio of a particle volume to the atomic volume, I may having a number of atoms within that particular volume. Here we should remember that we are putting a limitation in our model that the volume, whether the particle is a spherical or non-spherical, but its volume is same. That means let it be particle is, let us prism, but its volume will be equivalent of the spherical one only. In that case, I have a freedom to take the ratio of this one, that is the volume of a particle, that is 4 pi by 3 pi capital R cube, and there is a n number of atoms. So, n into 4 pi by 3 pi r cube, and that will be small r cube, and if I will take a ratio of that I will can having the number of available of atoms within the D shape or any shape of the particles, and equation 11 will give that information. That means available number of atoms in any particular shape of particle. Capital N will give the information that available number of atoms on a surface on any particular shape, because we are introducing the shape factor over here. Okay, so in this case what we have seen, the cohesive energy is basically a metallic nanoparticle is the sum of the bond energy, and therefore now I am putting the 1/2 into E bond, that is the bond energy, and bond energy multiplied by 1/2 factor. So, I wrote mention here that E bond is a bond energy, but the factor of 1/2 is giving you an idea that by having 2 atoms there would be a 1 bond, and therefore on an average it should be multiplied by 1/2. So, bond energy multiplied by 1/2 times of available number of candidates. So, this square bracket is giving us the information about the candidates, how much available. So, let us check it up one by one. So, 1/4 beta, beta is a correcting factor, because again as I said, for conceptual understanding we know the available number of atoms, but it is not always true that how many you can't consider all available number of atoms on the top. So, 1/4 beta 4 alpha small r square upon capital R square, that means the area of the non-spherical divided by the area of the spherical, that gives us a figure 4 alpha capital R square upon small r square, multiplying by the beta by 4, it is a correcting factor. 1/4 factor is basically arises because of a statistical understanding that it is available of occupying 25% of the sphericity. The second factor within the square bracket, that is giving us a difference of the total number of atoms minus the available number of atoms on the surface. So, we are also touching the atoms which are within the core. So, second factor is for the core representation, the first factor is for the surface representation. So, my above equation EP is EP dash is equal to 1/2 beta E bond, because beta is common. So, I am taking common this factor, that is a 4 alpha r square upon small r square, that you have seen in the previous equation number 2 or 3, that is nothing but the capital N, and therefore N divided by 4 into bracket total available number of atoms within the volume minus available number of atoms on the surface, because we have considering the atoms on the surface. So, we have to subtract it. So, this is the core factor, this is the surface factor, and therefore, my total energy in any particular shape of the particle, that would be given by E0 1/4 n plus 4n minus, so just expansion of the equation 12, and this 1/2 beta bond, that is factor is I am replacing by the E0, so that is here. So beta n 1/2 E bond, that is given by the E0, so that is over here. So it's a cohesive energy I am putting and that is simplified in the shape of E0 into the bracket 1 minus 3 by 4, because you can understand like this, you are taking a common 4n. When you taking a 4n common, that 4 get cancelled and n will be remain here. The idea behind is that because I having a number of candidates in the total volume as a out, then I may having a energy per volume also. So this is 1 minus 3 by 4, this is a surface factor, this is the volume factor, the n is replaced by this. So finally the shape of my equation will be E0 EP dash is equal to E0 1 minus 3 alpha small r upon capital R. Sometime equation will be asked in the shape of diameter, because diameter is more common with the particle. So r by 2, that is your d, denominator goes to numerator, so it becomes 6 alpha. So 6 alpha r by d. So equation 4 is our final equation. Okay, now we do have also the empirical relations. If you look at to the first graph or the first slide, many number of the observation empirical observed have, and there is some empirical relation has developed, and that is a melting point of a bulk is given by the 0.32 cohesive energy divided by the Boltzmann constant, and this is TMB, that is the melting temperature of a bulk. So equation 14, what you have seen in the last equation, that is a E0 1 minus 6 alpha r upon d, and that is the final shape of equation will be given as Tm 0.32, so that is over here 0 by E0 by k into bracket the equation 14 as it is. So this first factor is nothing but your bulk melting temperature, so I am replacing it the TMB. So ultimately melting temperature of melting point of nanoparticle is given as the melting temperature of a bulk times of 1 minus 6 alpha r by d. And again you can think of, if d is too larger than 100 nanometers, then this factor will be very small and you can neglect it. So you can say the melting temperature of the particle will be similar to the bulk material. That means above 100 nanometers you are not finding any particular significance importance of the sizing effect. But if it is smaller than this, then obviously you can having the equation 15 will give you the clarity about the melting point. So this is some mathematical understanding of it. You may having some kind of examples on basis of equation 14, equation 13, equation 9 and so on. Okay, thank you so much for paying attention. Stay home, stay safe. Shortly we will be uploading the second lecture as well.